Now we will solve an example related to the Poisson process. Starting at time t equals 0, suppose buses arrive at a bus stop according to a Poisson process at rate lambda equals 3 buses per hour. And people arrive at the same bus stop in order to get on a bus according to an independent Poisson process at rate mu equals 27 people per hour. We want to answer a number of questions related to this problem. Notice, first of all, that this is a merging operation of two independent Poisson processes. So, people plus buses is a Poisson process at rate 27 plus 3, which is 30 arrivals per hour. Okay? And one other thing to notice from the theorems that we proved in the previous two lectures is that each arrival is a bus, each arrival to this joint process is a bus with probability 3 out of 30, 1 over 10, okay? And a person with probability 9 over 10, okay? Now, accordingly, first of all, let's do part A. What is the probability that there are 4 people getting on the second bus? Okay, we're assuming, of course, that people who arrive at the bus stop will definitely get on the next bus that arrives. Okay, so under this assumption, what is the probability that 4 people get on the second bus? So if you think about this event, this is time t equals 0. This is the first bus. This is the second bus. And we are asking for basically 4 people to arrive in between the first and second buses. We don't really care how many people arrive before the first bus because they will have got on the first bus and left, right? So we're only interested in the event that there are 4 arrivals from people before the first bus to arrive after this point. But by the fresh start property of the Poisson process, notice that at this point, the joint process is restarting such that when viewed from this time forward, it is a Poisson process. And we're asking for the question that what is the probability that the next, what is the probability that of the next 5 arrivals to the joint process, the first 4 are people, and the 5th is a bus. Okay, but each arrival, as we argued, is a person with probability 9 over 10 and a bus with probability 1 over 10. So this is like Bernoulli trials, and the probability then is 9 over 10 to the 4 times 1 over 10, which is 9 to the 4 over 10 to the 5. Now, in part B, we will compute the expectation of the number of people getting on the second bus. Now, this is interesting because if we knew the amount of time, let's say T2 between the first and second buses, the expected number of people would be simply, well, 27 T2, because the rate of arrivals of people is 27. But we are not given the amount of time, so we are going to use iterated expectations. This is the expectation of the number of people getting on the second bus given T2. And the outer expectation is over T2. Okay, but this inner expectation is 27 T2. So we have the expectation of 27 T2, which is 27 times the expectation of T2, which is T2, well, lambda is 3 buses per hour. So the amount of time between between two buses is 1/3 hours, right? So this is 9. So the expected number of people getting on the second bus is 9. But how about the following? Suppose I arrive at the bus stop at time T0. So I just arrive at a random time T0, and I am curious about the number of people on the bus that I get on. Of course, when I arrive at T0, there may already be some people waiting at the bus stop who have arrived before me and after the last bus that left. And potentially there are going to be some people arriving after me and before the next bus. So I'm going to have to add the expectations of these people that came before me. Let's call that N sub B, and the people that come after me, let's call them NA. Okay, so the expected number of people that get on the same bus with me is the expectation of the number of people that come before me plus the number of people that come after me plus 1, of course, that's for me. Okay, but the expectation of the number of people that come after me by the fresh start property of the Poisson process, these are both equal to 9, because the situation is exactly the same as above. This is the expected number of people getting on the next bus, because whether I arrived at time T0 or not, I'm starting to observe the Poisson process at some fixed time T0, and the total number of people arriving before the first bus has expectation 9. Okay, so then the people that I observe on the bus other than me is 18, has the expectation 18. So the total number of people on my bus is 19, which is larger than 9, significantly larger than 9. So it's twice 9 plus 1. So what is going on? Let's rephrase this. The expected number of people seen by any person getting on a bus then is 19. But the expected number of people on a bus, that is the expected number of people seen by a bus driver, is 9. So this discrepancy is sometimes known as the random arrival paradox or random incidence paradox. It seems paradoxical. Of course, it is not a paradox because it just says that if you sample an interval at random, you are more likely to sample a larger interval. Now let's finally answer the question, what is the probability that the 12th arrival to the merged process of people and buses is the 3rd bus arrival? What is this probability? Well, now we are thinking of independent Bernoulli trials essentially. This is the probability of the event that there are 2 buses among first 11 arrivals and the 12th arrival is a bus. Okay, by independence of the Bernoulli trials, the first probability times the probability of the second part. We multiply the probabilities of these 2 events that we are considering the intersection of. So the probability of the first event is 11 choose 2, 9 over 10 to the power 9, and 1 over 10. And the probability of the second event is 1 over 10. So the answer is 11 choose 2, 9 to the 9, over 10 to the 3. In other words, 11 times 10 over 2, 9 to the 9, 10 to the 3, which is 11 times 9 to the 9 divided by 200. Okay.